Hi everyone, good evening. So let's start now. In this lecture, we will continue this asynchronous or ripple counter. Another name for asynchronous counter is ripple counter. So both are same. Remember, asynchronous counter, ripple counter. These two are same. Now let's start. So let me give you the summary of what we have seen in this sequential circuit. In the sequential circuit so far, whatever we have seen, let me give you the summary. Okay, and you tell me, so whatever has happened in the sequential circuit. So let me tell you that. Okay, so let's see. So we started sequential circuit. We started this topic, sequential circuits. This topic we started, and what we studied first, sequential circuits. This topic we started. Then first we studied what was the definition. Correct. First we saw the definition of sequential circuit. Do you understand the definition of sequential circuit? Tell me one by one. One by one, I am telling you all the things that we have seen, all the concept that we have seen. Now you tell me, do you remember the definition of sequential circuit? What is the definition of sequential circuit? That the output will depend, remember, at any point of time, at any time, the output will depend on the current input and also what is the state of the circuit. In the sequential circuits, every circuit has a state, and what that means, basically every circuit remembers, okay, every circuit remembers the history of past inputs and history of past outputs. So I can say that what is the definition of sequential circuit? Sequential circuit means a circuit in which output depends on what is your latest input, what is your current input, and also what was your previous output. Okay, what was your previous output? So this is the idea of sequential circuit. And you can notice the next topic we studied was, what was that? So sequential circuit needs a memory element, correct? In a sequential circuit, we need memory element. We need a memory element so that we can remember the previous output, so that we can remember the previous history. Okay, so this is the idea. So we need a memory element, and for the memory element, we started with the very basic memory element we studied. The very basic memory element we studied, what was that? The very basic memory element we studied, that was your SR latch. Okay, the very basic element memory element we studied, one was SR latch, another was S bar R bar latch. So these two we studied. Do you remember what was the most important point in SR latch? Do you remember what was the most important point? What was the most important, like on that point many questions come in the GATE exam. What is the most important point? The most important point about SR latch is that if both S comma R, so you can notice in SR latch, what is the most important point? In SR latch, you can notice this is your S, this is your R. So, and this is your next output. This is your next output. What this means? This is the next output. This is the next output. So if both are 0, 0, then the next output will be, it will be retain state. This is the retain state, means next output will be same as the present output. The next output will be same as the present output. So I can say this is what? This is your present output. So the present state, remember next output, or I can say state. So this is your present output, or I can call it state. This next output you can call it next state, and this present output you can call it present state. Okay, so if you have both S comma R 0, then it will basically no change. The state will not change. Okay, if this is 0, this is 1, then it means the reset will happen. If this is 1, this is 0, it means set will happen. And if both are 1, 1, then tell me what will happen? Can I say indeterminate? Can I say that indeterminate will happen? No, right? I told you that this is forbidden. I told you this is forbidden, but actually what will happen? Actually what will happen? So you can notice, let's call it Qn, and let's call it Qn bar. Let's also see Qn bar. So you can notice Qn bar will also be same, Q bar. Here it will be 1, here it will be 0. But when you have both 1, 1, then in this situation, what will happen? Both of them, they will become what? If both are 1, 1, then in this situation, both of them will become 0, 0. Correct? Yes or no? This we have already seen. SR latch. By default, SR latch is what? By default, SR latch, what it means? That means SR latch with NOR. Yes or no? That means SR latch with NOR. By default, when I say SR latch, then it simply means SR latch with NOR. So if the both the inputs are 1 1, then the output will, both the outputs will become 0 0. Okay, this qn and qn bar both will become 0 0. So in this situation, what I will say, this condition is forbidden. Remember, this condition is forbidden. Why this is forbidden? What is the reason why this is forbidden? Why this condition is forbidden? Why SR equal to 0 0 1 1 forbidden? What is the reason that this is forbidden? Tell me. The reason that forbidden is this. Okay, not because of this, not because of this, but because of what? Why this condition is forbidden? This condition is forbidden because what will happen after 1 1 if you apply 0 0? This transition, remember, after 1 1 if you apply 0 0, this transition will cause what? This transition will create what? Tell me. This transition creates uncertain. Okay, I can say uncertain state, or I can say basically indeterminate state. I can call it that this transition causes undeterminate state. This transition causes, we cannot determine uncertain behavior. Yes, very good. So this transition causes uncertain behavior, indeterminate behavior. Indeterminate behavior. Now remember, this point is very important because there are many questions in the GATE exam on this point. On this point, there are many questions. What many students think? Many students think that if you apply this, many students think this. Okay, many students, what they think? Remember, I am talking about SR latch. I am talking about SR latch. What many students think? Many students think that if I apply both of them 1 1, then this Q and Q bar, okay, this Q and Q bar, they will become indeterminate, like they will become indeterminate. So that many students think this, but this is wrong. Yes or no? That they will become indeterminate. This concept is wrong. This concept is wrong. What is the correct concept? The correct concept is when you apply 1 1, then both of them will become 0 0. They will definitely become 0 0. So no problem. They will definitely become 0 0. It is very much stable. It is a stable output. Okay, they will definitely become 0 0. But what is the problem? This condition is forbidden. I can say this input combination is forbidden, and the reason for forbidden is not this 1 1. The reason for forbidden is not this 0 0. The reason for forbidden is this transition. Okay, remember this point. So this is very important. Because of this transition, this is forbidden because of 1 1 to 0 0 transition. Because of this transition, it will happen. Correct? Do you remember? So we have already seen this. Similarly, in S bar R bar latch, what happens? Tell me. In S bar R bar latch, what happens? If I ask you, S bar R bar latch means SR latch with NAND. I can say that is SR latch with NAND. In this situation, what happens? In this situation, you can notice this 1 1 is the toggle. This is active low. This is active low. I told you. Okay, so this 1 1, sorry, this 1 1 is unchanged state. This 1 1 means unchanged state. If you want to do reset, then this will be the reset condition. If you want to do set, this will be the set condition. But when both are 0 0, then they both will become 1 1. They both will become 1 1, and this is forbidden. Why this is forbidden? Why this is forbidden? In this situation, this is forbidden. Like 0 0 is forbidden. Why this is forbidden? The forbidden is because of this transition from 0 0 to 1 1. Because of this transition, it is forbidden. Okay, so this is your S bar R bar latch. We have already seen. Now in the S bar R bar latch, again remember, this is your S bar R bar latch. In this S bar R bar latch, when both are 0 0, can I say this will be indeterminate state? No, this is wrong. Because remember what happens? What happens? When both are 0 0, then output will be stable. Output will be stable. Output will be 1 1. This is very stable output. But this condition, this input combination is forbidden. This input combination is forbidden. Remember, this input combination is forbidden because of this transition. After 0 0, if you apply 1 1, because of this transition, this input combination is forbidden. So this was the second point. So we have seen definition of sequence circuit. Then we have seen memory element, SR latch, S bar R bar latch. We have seen this, and then we started flip-flop. Okay, so this flip-flop concept we started. Then 4 flip-flops we have seen. There are total 4 flip-flops we have seen: SR, JK, D, T. Okay, So these things we have seen. What is a flip-flop? What are these SR flip-flop, JK flip-flop, D flip-flop, T flip-flop? All these things we have seen, correct? Okay. So these four flip-flop we have seen. JK, SR, T, D. These flip-flops we have seen. Now, tell me why this D? What is the meaning of this D? What is the meaning of this D? D, that is data. Because you are storing the data. If you want whatever data you want to store, just apply that, correct? Yes or no? Whatever data you want to store, just apply that data and that data will be stored. Okay. And this T means toggle. This T means toggle. Okay. And this J is similar to S. You can notice this J is similar to S and this K is similar to R. Okay. So this J is similar to set and K is similar to reset. So these things also we have seen. What was the next thing we have seen in the sequencer circuit? In the sequencer circuit, what was the next thing we have seen? The third thing. What was the third thing we have seen? Okay, so in the sequencer circuit, what was the next thing we have seen? In this sequential circuits. So we have seen all the flip-flops we have seen. Then fourth thing we have seen is flip-flop conversion. Correct? We have seen clock. Okay, what is the definition of clock? What is the behavior of clock? The clock terminology we have seen. The clock terminology. Okay, tell me. And then we have seen that some concept timing diagrams. These timing diagrams we have seen. These timing diagrams we have seen. Also, we have seen triggering mechanism. Triggering mechanism we have seen. We have seen flip-flop triggering mechanism. Now you tell me, this triggering, this is property of clock or flip-flop? This triggering, this is property of clock or flip-flop? So this flip-flop triggering mechanisms we have seen. Mechanisms we have seen. This is a property of flip-flop. This is not a property of clock. This is a property of flip-flop. So a flip-flop can be either positive edge triggered, level triggered, or I can say negative edge triggered or negative level triggered. But by default, flip-flop is what? By default flip-flop is what? By default, it is edge triggered. By default, flip-flop is edge triggered. So this edge triggering we have seen. Okay, we have seen. Now I told you one more thing. Flip-flop conversion we have seen. How to convert one flip-flop to another, that we have seen, correct? So this flip-flop conversion, many examples we have seen how to convert one flip-flop to another. And very important thing we also saw, what was that? How to implement this edge triggering. How to create a flip-flop which is edge triggered. How to create that? Tell me. Then we have seen how to create master-slave flip-flop we have seen. Very good. So this master-slave flip-flop we have seen. This master-slave flip-flop. This is equivalent to what? This is equivalent to negative edge triggered. I told you this master-slave flip-flop. This is equivalent to negative edge triggered flip-flop. This is equivalent to negative edge triggered flip-flop. Okay. So like this, we have already seen. Okay. So these concepts we have seen. We have seen the race condition in JK and T. This we have seen. The race conditions in JK comma T. Why it happens? Tell me. What is the reason this race condition happens in JK comma T? What was the reason? The reason is the first reason is level triggering. Remember, these are the reasons. Okay, if these are level triggered, then this will happen. JK comma T, if these are level triggered, then this will happen. This race condition will happen when they are level triggered. I told you this point. And the second condition, okay, so there should be level triggered, and what should happen? This toggle condition. In this toggle condition, okay, means when JK is equal to 1, when both are 1, or when T is equal to 1. This toggle condition, and what was the condition? That this, but actually this last condition is not much important, but anyway, you already know that this time period must be greater than propagation delay. Okay, this time, I can say this on period must be greater than equal to propagation delay. Okay, so these things we have already seen, but anyway, this is important. Okay, so these concepts, all these concepts we have seen. Now after that what was the next concept we have seen? After that we have studied the, okay, so flip-flop conversion, all the flip-flop, master-slave flip-flop, race condition, all these concepts we have seen. Timing diagram, triggering mechanism, clock terminology, all these concepts. After that, the next concept we studied was your timing constraints. We have seen the concept of timing constraints. This concept we have seen, timing constraints. Okay. Okay. So in this timing constraint, what we have seen what is hold time, what is setup time. So these concepts we have seen. Okay, these concepts, hold time, setup time, propagation delay. Okay, all these concepts we have seen. Next, after that, we studied something called finite state machines. So actually, we studied after this, we studied registers. We studied registers, and then we studied finite state machines. This finite state machine. In the finite state machine, we have seen what is Mealy machine, what is Moore machine. Okay, so these concepts we have seen. After that, we started counters. Okay, so our next topic was counters. Our next topic was counters. In the counters, I told you there are two types of counters. One is synchronous counters. One is a synchronous counters. So this was our next topic, synchronous counters and asynchronous counters. So these are the two counters. Now we have already seen this, but I will continue this asynchronous counter in this lecture, and then in the next lecture we will study this. Okay, this we will study in the next lecture. In this lecture we will study this one. So this is the summary of all the things that we have seen in the sequence circuit. Tell me, so far, do you have any doubt? Like all the concepts that we have seen, all the 12 concepts that we have seen, registers, finite state machines, Mealy machine, Moore machine, timing constants, hold time, setup time, flip-flop conversion, flip-flop, master-slave flip-flop, all these concepts, SR latch, S bar, R bar latch, all the concepts that we have seen. Did you understand all those concepts? Please tell me. Please tell me, did you understand all those concepts? Because remember, for these concepts like finite state, for these concepts, I have solved all the gate computer science and gate electronics questions I have solved for these concepts. All the gate CSE, all the gate ECE questions we have already solved. Okay, so let's move on now. Now we will continue our discussion on ripple counters, which is asynchronous counters. So we have already seen what is a register and counter. So you know what is a register, you know what is a counter. Tell me, what is this register? Which type of register is this? This is a register, but which type of register is this? Tell me the type of register. What is this register? No, every register is synchronous. Every register is synchronous. In every register, what happens? In every register, what happens? Tell me. In every register, what happens? Every register, whatever register you take, in every register, what happens? In every register, okay, remember, in every register, this happens that every flip-flop, they are operated by the same clock. Every flip-flop, they are operated by the same clock. Whatever flip-flop, so all the flip-flops, they are operated by the same clock. All the flip-flops are operated by the same clock. The same clock applies to all the flip-flop. This happens in all the registers. This we have already seen, this concept. Now you tell me, what is this register? What type of register is this? Many type of registers we have seen. Do you remember the type of registers? Like we have seen PIPO, parallel input, parallel output. We have seen SISO, serial shift registers we have seen. And we have seen a very special type of register from which gate exam questions come. In the gate exam, questions come from which register? From which register questions come? That we have seen, linear feedback shift register. Linear feedback shift register. Okay, linear feedback shift register, LFSR. So from that topic, a lot of questions come in the gate exam that we have already seen. All the questions we have solved. Okay, what is this type of register? This is your PIPO, I can say. This register is a PIPO because you are giving parallel inputs and you are getting parallel outputs. So there is no shifting here. So this is not a shift register. This is parallel input, parallel output register. There is no shifting here. So this is not a shift register. Correct? There is no shifting. There is no shifting here. So this is not a shift register. We have also seen what is a shift register. Shift register means you shift the information in either one or both direction. Okay, that is your shift register. So all these concepts we have seen. And what is a counter? The definition of counter is basically, okay, counter basically goes through a sequence of predetermined sequence of states. So this is the definition of counter. Counter will go through a predetermined sequence of states. Okay, there are two type of counters. One is asynchronous. This is asynchronous. Another name for asynchronous counter is ripple counter, and another counter is synchronous counter. So these are the two types of counter. Okay, let's move on now. So we have seen the difference. What is the difference between asynchronous counter and synchronous counter? What is that difference? The difference is very simple. In the synchronous counter, what happens in the synchronous counter? All the flip-flop, they are operated by the same clock. Yes or no? The same clock applies to all the flip-flop. The same clock, this same clock, remember the clock is same. The same clock is will apply to all the flip-flop. So the same clock is applying to all the flip-flop. All the flip-flop are operated by the same clock. Every flip-flop is operated by the same clock. In asynchronous counter, what happens? In asynchronous counter, you can notice the clock will apply to the first flip-flop. This clock will apply to the first flip-flop. This will apply to the first flip-flop, and you can notice the output of flip-flop 1 will operate as clock for the flip-flop 2. So you can notice output of this flip-flop will operate as a clock for the next flip-flop. So I can say output of a flip-flop will work as a clock for the next flip-flop. This is what happens in the asynchronous counters. Okay, yes. Now let's move on. Now we have seen the applications of flip-flop. What are the applications of flip-flop? These applications we have already seen, like application of flip-flop. One is shift register, storage register. Every register is a storage register. Okay, so this every register is storage register. So remember, every register, this is same as register. I can say every register is storage register, and another is shift register. Now we have also seen this application, frequency divisor. Yes or no? You can use flip-flop as a frequency divider. Now the chapter will start. Okay, now we will start our chapter. So let me start. So we have already seen that flip-flop, we can use flip-flop for frequency division. If you want to divide the frequency, then you can use flip-flop, correct? So application of flip-flop, that is, one is frequency division. And also, what is the benefit of, tell me, this frequency division will happen? And also you can produce perfect square wave. You can produce perfect square wave whose duty cycle is equal to 50%. So what is perfect square wave? Perfect square wave means duty cycle. Means I can say duty cycle is equal to 50%. Duty cycle equal to 50%. Okay, so this is the benefit. This is the application of flip-flop. So in this you can notice, tell me, if you want to, let's assume there is a clock signal with frequency f hertz. With frequency f hertz. Remember, hertz means per second. Remember, this means per second. So what it means? F hertz. What it means? It means f oscillations per second. It simply means s oscillations will happen. S oscillations will happen per second. Per second, these many oscillations will happen. Okay. So you have a clock signal with this much frequency. Then how can I generate another clock of half frequency? How can I generate a new clock, another clock? How can I generate another pulse of half frequency? So what I will do, I will use a T flip-flop. This we have already seen. So what you do, very simple, just this is your clock, just pass this clock through a T flip-flop. So when you pass this clock through a T flip-flop, then what will happen? The frequency will divide. I can say the frequency will become half. So this we have already seen. So you can notice here, whenever we pass this clock, this is your clock. So when we pass this clock signal through a T flip-flop, okay, then what will happen? We will get half frequency clock signal. We will get a signal of half frequency. Okay, this we have already seen. So I am just telling you, this is just a revision. So far we are only doing the recap. This is just a recap, because in the previous lectures we have already seen all these concepts. So you can notice the output of T flip-flop will divide the frequency of clock by 2. So T flip-flop is also called divide by 2 device. So you can call the T flip-flop. T flip-flop is also called divide by 2 device. Okay. Now tell me, can I use D flip-flop for frequency division? can I use D flip-flop for frequency division? Can I use D flip-flop? D flip-flop can I use? Yes, we can use. But remember, we can use D flip-flop, but remember, we will use it as a T. Actually, if you notice one thing, if you notice, can we use D flip-flop? Can we use D flip-flop for frequency division? For frequency division. Now, this interesting point is coming. This interesting point is coming that can we use D flip-flop as a frequency division? The answer will be yes. The answer will be yes. But if you notice one thing, we can use this D flip-flop as a frequency division, but this D flip-flop we will use as a T. Can you notice? But D flip-flop will be used as T. Will be used as a T. Yes or no? This will be used as a toggle flip-flop. The setting of D flip-flop I will do as a toggle flip-flop. This is the point. We will use it as a toggle flip-flop. What we will do? Tell me. If I want to use this D flip-flop as a frequency division, this is my clock. Let's assume this D flip-flop is positive edge triggered flip-flop, and this is your clock. This is your clock. Okay, let's assume this is your clock. Now tell me what will happen. So this is the clock. The clock is this. Now what you will do? If you want to use this D flip-flop as a frequency divider, then what you will do? You will use this as a T flip-flop. You will use this D as a T flip-flop. So what I will do, tell me which connection I should make. I should make this connection. This Q bar will be connected to D. This Q bar will be connected to D. Okay, Q bar will be connected to D. Very good. Okay, so you can notice that one thing you can notice that I can use D flip-flop as a frequency for frequency division, but the important point is that this D flip-flop I will use as a toggle flip-flop. Correct? I am using this D flip-flop as a toggling device. As a toggling device, I am using it. So ultimately, what I am taking? Ultimately, basically, I am using this toggle feature I am using. Yes or no? Ultimately, I am using this toggle feature. This toggle feature I am using. Similarly, can I use JK flip-flop as a frequency divider? Can I use JK flip-flop as a frequency divisor? The answer again is yes. The answer again is yes, but the same point will happen. What will happen? JK will be used, but the toggle feature of JK will be used. I can say toggle feature of JK will be used. So this toggle feature of JK will be used. Toggle feature of JK used. Okay, so ultimately this JK I am using as a toggle. Okay, so this is your JK. This JK, ultimately this JK I am using as a toggle. Let's assume this is clock. This is your clock. And this JK, what I will do? I will use this JK as a toggle. So what I need to do? If I want this toggle feature of the JK, then what I need to do? I need to connect both of them to 1. Okay, I need to connect both of them to 1. This is what I need to do. Okay, now you can notice this JK flip-flop is working as a T flip-flop. This JK flip-flop is also working as a T flip-flop. Okay, yes or no? So this is the reason T flip-flop is called frequency divider. This is the reason. Can you notice? See, are you getting my point? You can use JK flip-flop, you can use D flip-flop, you can use SR flip-flop for frequency division. For frequency division, you can use anything. But the point is what? The point is that whatever flip-flop you use, you will use the toggle feature. Yes or no? Basically, whatever flip-flop you use, you will use it as a toggle flip-flop. Okay, so that is the reason. This is the reason this T flip-flop is called frequency divider. This T flip-flop is called division by 2 device. Okay, so this is the idea. And remember, the output will be perfect square wave. The output will be perfect square wave. This we have already seen. Okay, let's move on. How will you solve this question? How will you solve this question? So, this is the question. First, let's create a divide by 2. Build a frequency divider, divide by 2 using D flip-flop. So using D flip-flop, what I will do? Using D flip-flop, what I will do? I can make this connection. Basically, the complement of this I will connect here. The complement of this I will connect here. Correct? Okay, so what I will do, basically I will, the complement of this I will connect here. This is what I will do. The complement of this Q I will connect here. So like this I will do. Or what I can do, I can directly connect this to D, or I can directly connect this to D. Okay, either I can do this. Now, anyway, this is fine. So like this. And how to create JK? Very simple. So this one, I will use this. Okay, both of them, one more. Now, so this is the idea. Now let's see how to create divide by 4 circuit. How to create divide by 4 circuit. Then what you will do? You can use 2D flip-flop. You can use 2D flip-flop. You can use another D flip-flop. Okay, so this another D flip-flop you can use. So because the first D flip-flop, what it will give you? The first D flip-flop. So you can use 2D flip-flop. The first D flip-flop will give you frequency divided by 2. Yes, correct. The first D flip-flop. So if this clock has frequency F, then first D flip-flop will give you frequency F by 2. This you can give as an input. This you can give as a clock. This you can give as a clock. Remember, this you can give as a clock. This you can give as a clock. Okay, so this you can give as a clock. This F by 2 frequency, this you can give as a clock. Correct? Don't give this as an input. Yes or no? Do you, okay, please see. Don't give this as an input. Like, don't make this setting. Don't make this setting. Like, don't do like this. Don't do like this. Correct? What I need to do? What I need to do? I need to connect this as a clock. So this I will give as a clock. The output of the first D flip-flop. The output of the first D flip-flop, I will give as a clock to the next D flip-flop. This is what I will do. Correct? And this setting is same. Okay, so that's it. Very simple. Now, if I do like this, then what I will get? If I do like this, then here, this will give me F by 4. This will give me F by 4. The output of the second D flip-flop will have frequency F by 4. This is the idea. Very simple, correct? Similarly, you can create using JK. Using JK, what you will do? The same thing you will do. This is your JK. The same thing you will do. This is your JK. Okay. Now, what you will do? First, you will connect both of them to 1, 1. This you will connect to 1, 1. Then, will you connect like this? Tell me, will you connect like this? No. You will give this as a clock. This you will give as a clock. This you will give as a clock. This you will give as a clock. And this J will be connected to 1. This K will be connected to 1. Now you can notice that here you have the frequency F by 2. And here you have the frequency F by 4. Okay. So like this you can do. Like this you can create frequency divider by 2. So this is the idea. And how will you create frequency? How will you divide frequency by 2 power K? How will you divide frequency by 2 power K? So what you will do? You will connect basically K T flip-flops you will connect. Okay, total K T flip-flops you will connect. So there will be this T flip-flop, this T flip-flop. So these K T flip-flop, total K T flip-flop you will connect. This I can say T1, this is T2. Let's call it TK. Let's call it TK. So now this clock, this is your clock. This clock, let's assume this clock has frequency F hertz. If this clock has frequency F hertz, you will connect 1. Remember, you will connect 1. You will connect every T to 1. Every T will be connected to 1. Every T will be connected to 1. Okay, so this 1, every T will be connected to 1. Now, this output will go as a clock to this. I can say this output will work as a clock to this. This output will work as a clock to this. This output will work as a clock to this, and so on, and so on, and so on. This output will work as a clock to this. Okay, like this will happen. So finally, what will happen? You can notice here the frequency is F by 2. Here the frequency will be F by 4. So here the frequency will be F by 2 power K. So you can connect K T flip-flops. Very simple. Okay, all these concepts, these are very simple concepts. We have already seen all these concepts. Correct. So we have seen that flip-flop can be used as a frequency divider. Is there any other application? We have seen what we have seen. We have seen that flip-flops. We have seen that flip-flops. This application we have seen. What is this flip-flop? Which application we have seen? As a frequency divisor. We have seen this application as a frequency divisor. If you want to create a frequency, if you want to divide frequency by any power of 2, you can do that. Okay. Next, so frequency divisor. Another application what we have seen, tell me. This is the first application we have seen. Another application we have seen, that is can produce perfect square wave. If you want to produce perfect square wave, you can do that. If you want to produce perfect square wave, means duty cycle equal to 3. Duty cycle equal to 50%. Then you can do that. Remember, in the T flip-flop, if this is your T flip-flop, if your clock is not perfect, like for example, if your clock is not perfect, let's assume your clock is not perfect, like I can say duty cycle is not 50%. Okay, maybe your clock can be like this. Maybe your clock can be like this. So let's assume this is the clock. Let's assume this is your clock. This is the clock. Okay, so if this is the clock, now tell me what will be the output of this T flip-flop. The output of this T flip-flop, that will be a perfect square wave, and the frequency will be half. So here, if the frequency, remember here, if this time, if this is time T, if this time is T, this is your time period. If this time is T, that means time period. That means time period. Then what will happen to the output? The output time period, what will be that? That will be twice of T. That will be double of T. So the output will be a perfect square wave. Let me tell you, the output will be a perfect square wave. It will be a perfect square wave. You can check it out. We have already seen this. It will be a perfect square wave. And this time period, what it will be? This time period, what it will be? Tell me. This time period, this will be 2T. Correct? This will be 2T. So you can notice here, if the time period is T and the frequency will be what? Here the frequency will be 1 by T. Frequency will be 1 by T. If the time period is T, then frequency will be 1 by T. So here the frequency will be what? Here the frequency will be 1 by 2T. So you can notice frequency is f by 2. Okay, frequency is basically f by 2. Is this clear? So we are getting a perfect square wave, and this we have already seen in the previous lectures. Okay, this concept we have already seen in the previous lectures. You can watch the previous lectures. There I have already told you that it will create a perfect square wave. So these are the two applications that we have seen. Now, what is the next application? The next application is counting. This is the next application. The next application is counting. We want to create counters which will count, which will do the modulo counting. What this means, modulo counting? First of all, what is this modulo counting? This we have seen in theory of computation also. What is a modulo counting? Modulo counting means basically you start. Modulo counting means you start. Okay, and then you basically again after some time, okay, this will repeat. After some time, this will repeat. So this is the wrap around. I can say this type of, I can say that this type of counting, this is called modulo counting. This type of counting is called modulo counting. Okay, wrap around. So this type of counting we call it modulo counting. So this, if this type of counting you are doing, then we will call it modulo. Then we will call it modulo n counter. Why modulo n counter? Sorry, this will be called modulo n plus 1 because there are n plus 1 states. So this will be modulo n plus 1 counter. Yes or no? This counter will be called modulo n plus 1 counter. Why? What is the reason? Because n plus 1 states you have. N plus 1 distinct states you have. So this counter will be called modulo n plus 1 counter. Okay, and similarly, if you want modulo n counter, then you can basically, I can say that you can start from S1. Okay, so you can start from S1. Now this is a modulo n counter because there are total n distinct states. So this is the another application of flip-flop, that is counting. Let's see how to do the counting. You can see this circuit will do the frequency division, correct? Yes or no? Agree? So this circuit will do the frequency division. So definitely it will do the frequency division. But how can we read this as a counter? Is this a counter? Is this a counter? See, this will divide the frequency that we know. It will definitely divide the frequency that we know. But how can we interpret this as a counting? How can we interpret this as a counter? So very easy, because it will basically go from this. If you see this T flip flop, this is your T flip flop, okay, and whatever clock you have, now you can notice this output. Look at this output, this state. Output means state. Output, that is same as state of the flip flop. So you can notice that what are the outputs? The output will go like this. This is your, let's assume you are in the state 0. Then after one clock pulse, what will happen? After one clock pulse, after one rising edge, because this flip flop is positive edge triggered. Remember, this flip flop is a positive edge triggered. This is a positive edge triggered. And because this flip flop is positive edge triggered, so what will happen? It will happen that if the state is 0, then after one clock cycle, what will happen? This will become 1. After one more clock cycle, after one more rising edge, it will become 0, and so on. So you can notice this modulo counting is happening or not. I can say this is your modulo 2 counter. So this is your modulo 2 counter. Okay. So you can notice this circuit. If you notice the previous circuit that we have seen, the previous circuit, which is T flip flop, which is a T flip flop. So the previous circuit that we have seen, what is that? That is a frequency divided by 2. That is a modulo 2 counter. And I can simply call it divide by 2 counter. Yes or no? So T flip flop, you can use as these 3 features. So the another name for T flip flop, I can say that T flip flop, you can use this T flip flop as a frequency divider by 2. You can use this as a modulo 2 counter. You can use this as a divide by 2 counter. Divide by 2 counter simply means frequency divide. Okay. So all these concepts we have seen. Now, similarly, if I have, let's assume, if I have 2 counters back to back, if I have 2 counters, then what it will do? If I have 2 counters, like for example, let me take 2 counters. If I take 2 T counters back to back, okay, let's call it T0, let's call it T1, and let's assume this is the clock here, and this is connected to 1, this is also connected to 1. What I'm doing, the output of this I'm connecting to the connecting as a clock to this, output of this as a clock to this. Okay, so, and this is your Q1. Now you tell me, so if I do like this, so this is your system clock, and this is your Q0, and this Q0 is acting as a clock for this next T flip flop. Okay, so in this situation, both are, I can say that both are your both are positive edge triggered flip flop. Now in this situation, let's make the timing diagram. Let's understand by the timing diagram. So what will happen? So first of all, this Q1, what is the frequency of this Q1? If this clock has frequency f, if this has frequency f, then what will be frequency of this? It will have frequency f by 2. Okay, this you already know. It will have frequency f by 4, and this will have frequency f by 2. Okay, this will have frequency f by 2. But what is the counting sequence? Find the counting sequence. The question is, find the counting sequence. What will be the counting sequence here? What will be the counting sequence? After 0, 0, where you will go? Let's see. Okay, so for that, let me create a timing diagram. Without timing diagram also you can do. If you don't want to create timing diagram, then also you can do. But let me create a timing diagram. So let's see. Let's assume this is the clock. Let's assume this is the clock. So your clock is, let's assume, like this. So you have clock like this, let's assume. And these flip flops are positive edge triggered. Remember, these flip flops, these are positive edge triggered flip flops. Okay. So all the flip flops that we have. So this clock is applying to LSB. So let's assume this is LSB. Let me assume this is LSB, and let me assume this is MSB. Now what will happen? So this Q0, what will be the Q0? What will be the waveform for Q0? the Q0 waveform. Let's assume initially both are 0, 0. This Q0 and Q1 both are initially, let me assume both are 0, 0. Initially, I am assuming that both are 0, 0. Initially this is also 0. Initially this is also 0. Let me assume. Okay, now you can notice both the flip-flop are positive edge triggered. Both the flip-flop are positive edge triggered. But tell me, when this Q1 will, when this Q0 will change, remember T0 is connected to 1 and this T1 is connected to 1. So here what will happen? Tell me what will happen here. One interesting thing you can notice that when this, remember this is directly connected to clock. Can I say this is directly connected to clock? Now when the clock will go, remember this is positive edge triggered. This is positive edge triggered. So when the clock will go from 0 to 1, when the clock will go from 0 to 1, then what will happen? When the clock will go from 0 to 1 and then this T0 is connected to 1. So then it will toggle. Then Q0 toggles. Can I say? Then Q0 will toggle. Very good. Okay. Now you tell me when the clock will go. Can I say when the clock will go from 0 to 1? Can I say Q1 will also toggle? Can I say Q1 will also toggle when the clock will go from 0 to 1? When the clock is going from 0 to 1, then can I say Q1 will also toggle? No. What is the reason? What is the reason? Because this clock is not applied on this T1. On this flip-flop, this clock is not applicable. What is the clock for this T1? This is the clock for this T1. This is the clock for this T1. Clock for T1 is this. So what I can say? I can say that when this Q0, remember clock for T1 is Q0. Clock for T1 is Q0. So I can say that when Q0, remember, but this is positive edge triggered. But this T1 is positive edge triggered. You can notice this is positive edge triggered. You can notice this is positive edge triggered. So what it means? This is positive edge triggered. So what that means? It means when the Q0 will go from 0 to 1, then Q1 toggles. When Q0 will go from 0 to 1, then the Q1 will toggle. Very good. Okay, excellent. Now you tell me. So initially I am assuming that both are 0, 0. Let me assume both Q0 and Q1 are 0, 0. Now you can notice that Q0 will toggle with every clock pulse. With every rising edge, Q0 will toggle with every rising edge of the clock. This is your clock. This is your clock, I can say. So let's assume, let me write it. So this is your clock. Okay. Now with every rising edge, what will happen? This will toggle. With every rising edge, this will toggle. With every rising edge, this will toggle. Okay. Now, so this will happen with Q0 because you can notice the Q0 will toggle when the clock is, for every rising edge of the clock, Q0 will toggle. The reason is simple, because clock is applied on this flip-flop. Okay, clock is applicable on this flip-flop. So that is the reason I can say, and this flip-flop is a positive edge triggered. So I can say when the clock will go from 0 to 1 and this input is T is equal to 1, this T equal to 1, this is fixed. It means this output will toggle for every rising edge. For every rising edge, the output will toggle. Okay, very simple, extremely simple. Now you tell me, when the Q1 will toggle? Q1 will toggle in this situation when Q0 is going from 0 to 1. When Q0 is going from 0 to 1, then now in this situation, this Q1 will toggle. So this Q1 will toggle in this situation. This Q1 will toggle in this situation. And so on. Now you notice. So you can notice both are initially 0, 0. From 0, 0, where are we going? Remember, this is MSB. Please understand, this is MSB. And remember, this is LSB. Okay, so now you tell me. So from that, they are going to 1, 1. Now they are becoming 1, 1. So from 0, 0, they are becoming 1, 1. Yes or no? From 0, 0, they are becoming 1, 1. Now, after that, what is happening? After that, what is happening? So from 0, 0, they are becoming 1, 1. And after that, what is happening? This is G, so they are, remember MSB is this. So they are becoming 1, 0. They are becoming 1 0 because MSB is a Q1. So they are becoming 1 0. After that, what is happening? They are becoming 0 1. After that, they are becoming 0 1. And after that, 0 1. After that, both are 0 0. After that, both are 0 0. After that, both are 1 1. So this is the counting sequence. Yes or no? The counting sequence will be like this. Okay, 1 1 1 0. So like this. What is this? What is this counter? What is this counter? This is a binary down counter. Can you notice? This is a binary down counter. Down counter. Down counter. Yes or no? This is a binary down counter. Means it is going from it is going from 3 to 2, from 2 to 1, from 1 to 0, and from 0 to 3. So this is a binary down counter. Remember. Is this clear? Let me know. So this point is clear to everyone. This is a binary down counter. So you did a mistake, right? Yes or no? Some of you were saying from 0 0 to 0 1, then 1 0, then 1 1. Some of you were giving the answer binary up counter. You were giving the answer binary up counter from 0 to 1, 1 to 2, 2 to 3. Some of you were giving this answer. Correct or not? So take care. Is it clear? Take care about this. Don't worry. I will explain a very nice idea. I will explain. After that, you don't need to create this timing diagram. Okay, you will never have to create this timing diagram, but this timing diagram is for understanding purpose. So did you understand whatever we have seen so far? Tell me, did you understand this timing diagram? Did you understand? Remember, both the T inputs are 1 1. It means in every clock cycle they will toggle. Both of them will toggle. This will toggle when clock is going from 0 to 1. This will toggle when Q0 is going from 0 to 1. Okay, so this Q1 will toggle when Q0 is going from 0 to 1. So like this counting sequence you will get, and this is your binary down counter. One more interesting thing. What is that? One more interesting thing. That is, what is that interesting thing? What is the frequency of this? You can notice here the frequency here. If you notice here the frequency is T. Sorry, here the time period is T. Here the time period is T. Here if the time period is T, this time period, this is T. Now tell me, what is the time period of Q0? In one time period of Q0, there are two time periods of clock. In one time period of Q0, there are two time periods of clock. Can I say? So I can say this will be 2T. This will be 2T. And similarly, in one time period of Q1, there are four time periods. There are four time periods of the clock. So what I can say? I can say, what is the frequency of Q2? What is the frequency of Q2? What is the frequency of Q2? That I can say that is half the frequency of Q0. That is half the frequency of Q0. Half the frequency of Q0. Okay. And I can say that is 1/4 of the frequency of clock. Frequency of clock. Correct or not? Yes or no? Let me know. So you can notice in one time period of Q0, there are two time period of clock. In one time period of Q1, there are four time periods of the clock. There are four time periods of the clock. There are four time periods of the clock. So I can say that the frequency of Q1. Sorry, this is Q1. The frequency of Q1 will be half the frequency of Q0, and that will be 1/4 the frequency of a clock. Very simple. Now, what happens in the real life? So here we are assuming, so far what we have assumed. So here we are assuming there is no, can you notice here we are assuming there is no propagation delay. Assuming no propagation delay. Here we are assuming that there is no propagation delay of any flip-flop. Correct? So in this situation, we are assuming that there is no propagation delay of any flip-flop. But in the real life, what happens? Tell me. In the real life, what happens? There is propagation delay. But okay, but there is propagation delay. But in real life, okay, in reality, every flip-flop has a propagation delay. Every flip-flop has a propagation delay. Every flip-flop will have some propagation delay. And you know the definition of propagation delay. What is that? What is that? When input changes, output will change after some delay. When input changes, output will change. Output will change after some delay. After some delay. So if the input is changing here, for example, if the input is changing here, if the input is changing here, then the output will change after some delay. Output will change. Output will change, but after some delay. Okay, so this delay, the output will change. When the input is changing, the output will change after some delay. This is the definition of propagation delay. This time period, this period is called propagation delay. So when the input is changing, when the input will change, output will change after some time, after some delay, very small delay. But you can notice every flip-flop has a propagation delay. Now, if I consider propagation delay, now what will be the waveform? Now you tell me what will be the waveform if I consider propagation delay. So assume that propagation delay is there. Assume propagation delay of a flip-flop is there, and that is some maybe t. Okay, let me assume that is t. So assume propagation delay of flip-flop, every flip-flop is t. Now what will be the waveform? Now what will be the waveform now? Now what is going to be the waveform? So you can notice I am assuming initially Q0 is 0. So when the clock, initially Q0 is 0, correct? Initially this Q0 is 0. Now when this clock on, okay, so this Q0 will change. This Q0 will toggle. Will it toggle immediately? Tell me. Will it toggle immediately? No. It will toggle after some delay. There will be some delay. There will be some delay after that delay. So there will be some delay. There will be some delay. After that delay, it will change. Okay, next here it should change. Here it should change. It should change, but it will change after some delay. It will change after some delay. After some delay, it will change. Next, here it should change. Here it should change, but it will change after some delay. It will toggle after some delay. After some delay. After some delay. Yes or no? Correct? Did you get it? Okay, this will happen, correct? Now tell me. So this, what about this Q1? This Q1 will change on the rising edge of Q0. When Q0 is going from 0 to 1, when this Q0 is going from 0 to 1, then Q1 will toggle. So the Q1 should toggle here, yes or no? Can you notice Q1 should toggle here when the Q0 is going from 0 to 1? When this Q0 is going from 0 to 1, then Q1 should toggle. But there is a propagation delay, so it will toggle after some delay. It will change after some delay. Okay, again it will change. At this time it should change. At this time it should change, but it will change after some delay. Okay, and so on and so on. At this time it should change. At this time it should change, but it will change after some delay. Okay, so now you tell me one thing, very interesting thing. Very interesting thing will happen now. So what is happening here? In this diagram, if you notice, what is the sequence? Initially both are 0 0. Initially both are 0 0. Then from 0 0 they should go to 1 1, right? You agree they should go to 1 1, correct? They should go to 1 1. If there is no propagation delay, they must go to 1 1. They must go to 1 1. They must go to 1 1. But what is happening here? They must go to 1 1. But what is happening here? So you can notice that for a moment, look at this period. Look at this period. Look at this period. For a moment, for a very small moment, what is happening? This is 1, this is 0. For a small moment, look, for a small moment, this will go to 0 1 because this is MSB. This is MSB. So I can say that for a small moment, it will go to 0 1. For a very small moment, yes or no? Correct? For a very small moment, for a very small moment, what will happen? Okay, from 0 0, it will go to 0 1. Okay, correct? After that, it will go to 1 1. After that, it will go to 1 1. This will happen. Definitely this will happen, right? In the real life, definitely this will happen. Okay, now tell me. So after this, you can notice after 1 1 where it should go, where it should go after 1 1 where it should go to 1 0. And you can notice, will there be any this type of state is called glitch, or you can call it transient state. This type of state is called transient state. Okay, this transient state is basically a glitch, I can say. It is a glitch. It is called transient state. This is momentarily. This happens only momentarily. For a moment this happens. Okay, for a moment this happens. So we call it transient. Now you tell me, from 1 1 to 1 0, will there be transient state? Will there be any transient state? No. Why? What is the reason? What is the reason this transient state is coming? What is the reason this transient state is coming? Because 2 bits are changing. Because 2 bits are changing, you can notice first LSB will change, then MSB will change. Correct or not? Please understand why this transient state is coming. Why this transient state is coming? Because first LSB will change, then MSB will change. Correct or not? First LSB will change, first LSB will change, first LSB will change, then MSB will change. So this is the reason this transient state is coming. But here you can notice there will be no transient state, and you can check from the transition diagram. You can verify from the transition diagram there is no transient state. Correct or not? From the transition diagram, can you notice in the transition diagram there is no transient state? Okay, very good. Now tell me, from here where you should go? From here, from this state, where you should go? You should go to this state 0 1. You should go to this state 0 1. Will there be any transient state? Will there be any transient state? Yes, there will be a transient state. Which transient state? Without looking at the timing diagram. Without looking at the timing diagram, you tell me what will be the transient state without looking at the timing diagram. First LSB will change, then MSB will change. First LSB will change, right? First LSB will change, then MSB will change. So first LSB will change, then MSB will change. So transient state will be 1 1. So remember, is this clear? And you can notice from the transition diagram. In the transition diagram also this is happening. In the transition diagram, for this moment, for this small moment, what is happening? For this small moment, look at this moment. This is 1, this is 1. For a small moment, this is 1, this is 1. Then they will become 0. Okay, then they will become, and from here to here there will be no transient state. You can notice there is no transient state. There is no transient state. So I hope this point is clear. What are the transient states and why are they coming? Did you understand? Why are they coming? So what are the transient states? Why are they coming? Why transient states? What is the reason transient states are coming? Why these transient states in asynchronous flip-flop, sorry, in asynchronous counter, in this asynchronous counter, why these are happening? What is the reason? What is the reason why these transient states in asynchronous counters? They will not happen in the synchronous counter. They will happen in asynchronous counter, and the reason is because of propagation delay. Due to propagation delay. But there is another reason. Due to propagation delay. But remember, these transient states will not be present in synchronous counter. They will not be present in synchronous counter. So due to propagation delay of flip-flop, that is fine. But this propagation delay will be in the synchronous counter also. Do you agree? Yes or no? The propagation delay of the flip-flop will be in the synchronous counter also. In the synchronous counter also, you will have the propagation delay. So propagation delay is one factor. But what is the another factor? The another factor is important. The another factor is that this LSB, this flip-flop, this LSB is directly changing because of clock. See, this LSB is changing because of clock. Because of clock, this LSB is changing, and because of change in LSB, MSB is changing. Because of change in LSB, MSB is changing. So first LSB will change. So because of clock, LSB will change. Because of change in LSB, MSB will change. Yes or no? One after another. Do you agree or not? First LSB will change. I can say because of clock. Because of clock. Okay, first LSB will change. First this LSB change. First this LSB changes in every cycle. This LSB will change in every cycle, you know. So because of clock, this LSB will change. Now, because of this change, what will happen? Because of this change, remember, I can say because of this change in LSB, because of the change in LSB, what will happen? Because of this change in LSB, because of this change in LSB, MSB will change. MSB changes. So one after another, this is happening. First LSB changing, first LSB changing. Okay, then I can say then MSB changing. So first LSB changing, then MSB changing. So this is what is happening. So this is the reason. This is the reason what will happen. This will happen. This is the reason these transient states are coming. Is that clear? So this is the reason these transient states are coming. You can notice these are the transient states. So one transient state is this. So this you can notice 0, 1. Okay, so anyway, so you know, you understood this, that these transient states are coming. Correct? So we have seen this. So now tell me one thing. If you have, so you understood this point you understood. So what is happening? So from 0, 0, if you have binary up, if you have binary down counter, if you have binary down ripple counter, because this is a asynchronous counter, yes or no? This is binary down a ripple counter. So in binary down ripple counter, what will happen? This is your 0, 0. If there is propagation delay, if there is propagation delay, if no propagation delay, if there is no propagation delay, then there is no problem. If there is no propagation delay, there is no problem. Then this, okay, then it will happen 1, 1, and then 1, 0, and then 0, 1, and then this, if no propagation delay. But if there is propagation delay, if we have propagation delay, some propagation delay, if propagation delay of flip-flop is equal to some time t, then what will happen? Then this will happen. See, from this state, where will you go, tell me? From this state, you should go to this state. You should go to this state, but for a moment, you will go to this state. Why? What is the reason? The reason is first LSB will change. First LSB will change. First LSB will change. Okay. And then MSB will change. First LSB will change, and then MSB will change. Then MSB will change. Yes or no? So this will happen. Now from 1, 1, there is no problem. There is no problem. There is no transient state. So here there is no transient states, because only one bit is changing. So no transient state. From here you should go to 1, 0. Sorry, 0, 1. You should go to 0, 1. But what will happen? First this LSB will change. First this LSB will change. Then this MSB will change. Okay. So, and from this you can directly go here. So like this. How many transient states are there? How many total transient states are there? Total 2 transient states are there. Total 2 transient states we have. Okay. So very simple. Hopefully this point is clear. Okay. Now let's move on. Now let's let's start. Okay. So actually this is the concept. This is the whole concept. This is your asynchronous counter. Now let's take some more examples. Now we are going to take more examples, more and more examples we are going to take. Okay. So, but the same concept, remember, whatever we have seen so far, that same concept we will apply again and again. Okay. The same concept we will apply. But before that, let's see asynchronous counter. The another name is ripple counter. Another name is ripple counter. Another name is ripple counter. Okay. These are same. Now, what is binary counter? First of all, first we need to study what is binary counter. What is the definition of binary counter? I told you this. Do you remember the definition of binary counter? Binary counter. This is a counting sequence. Binary counter. What is the definition of binary counter? Tell me, what is the definition of binary counter? This type of counter is binary counter. Like this type of counter, which will go from 0 to 1, from 1 to 2, from 2 to 3, and so on. Okay, 2 power n minus 1, and then it will go to 0. This is called binary counter. By default, binary counter is binary up counter. Binary up counter. Okay, so what is a binary counter? Remember, this is the definition. This is the definition of binary counter. So what is the definition? Here, let me tell you. For example, 3-bit binary counter, what that will be? If I ask you 3-bit binary counter, what that will be? 3-bit binary counter. Okay, 3-bit binary counter, what that will be? That will be like this. It is a binary counter. It is a binary counter. It is 3-bit binary counter. So it will go from 00 to 001. Then from that, it should go to 010. Then it should go to 011. This is the counting sequence. Remember, this counting sequence is called binary counter. Then 100, then 101, then 110, then 111, and then this. This is called binary counter. Is this clear to everyone? Tell me. This counting sequence is called binary counter. This can be implemented in 2 ways. We can implement this in 2 ways. This we can implement in 2 ways. What are those? This we can implement in 2 ways. This we can implement in 2 ways. What are those? One is asynchronous counter, in an asynchronous manner. Okay, using asynchronous counter. So remember, this is your binary counter. This counting sequence. This counting sequence is called. Remember, this counting sequence is called binary counter. Okay. So you can implement this either as a asynchronous counter, or you can implement this as a synchronous counter. Clear? Tell me, is this clear? So either we can implement this as a asynchronous counter, or we can implement this as a synchronous counter. But this is the definition of binary counter. If anyone asks you what is binary counter, this counting sequence is called binary counter. So binary counter is this counting sequence. This counting sequence is your binary counter. The implementation can be different. Yes or no? Do you agree or not? The implementation can be different. This counting sequence is called binary counter, 3-bit binary counter. But the implementation can be either you can implement as a asynchronous counter, or you can implement as a synchronous counter. The implementation can be different. Similarly, there is something called binary down counter. There is something called binary down counter. What is this binary down counter? What is the definition of binary down counter? It is like this. Basically, it is, I can say, from maximum it will start. From maximum it will start, and then it will go down. Then it will go down. Okay, it will go down. So it will definitely, it will go like this. It will go down. Like I can say 3, then 2, then 1, then 0, and then this. So this is called binary down count. So what is 3-bit binary down count? Tell me. What is 3-bit binary down counter? What, or I can, 3-bit binary down counter. That will be from 1-1. This sequence is called 3-bit binary down counter. 1-1, then it will go to 1-1-0, then it will go to 1-0-1, it will go to 1-1-1-0-0, it will go to 0-1-1, it will go to 0-1-1, then 0-1-0, and then 0-0-1, and then 0-0-0, and then this. Remember this sequence, please understand this sequence is called binary down counter. This sequence is the binary down counter. And what are the implementations? How can we implement this? What are the implementations? What are the implementations? There are 2 implementations. Either you can implement it as an asynchronous counter. Another name is ripple counter. You can also call it ripple counter. The another name of asynchronous counter is ripple counter. Or you can implement this as a synchronous counter. That is your choice. Okay, either you can implement like this, or you can implement like this. But this sequence is called binary down count. I hope this point is clear. Okay, so this is the idea. This is the idea of binary counter. Now we will implement the binary counter. Let's start now. First, what we will see first? Which implementation we will see? Asynchronous. First, we will see Asynchronous implementation. This is what first we will see. First we will see binary counter. This is what we are going to study now. Binary counter, asynchronous binary counter. This is what we are going to study now. So this is the next topic. The next topic will be asynchronous binary down counter. I can say asynchronous binary counter, or I can say first we will study binary down counter. So first let me check binary down counter, then we will study binary up counter. Okay, so this is your another name. What is the another name? We can also write like this: binary down ripple counter. Another name is binary down ripple counter. Okay, so this is the another name. Both are same. Okay, let's see this. Let's study this. So let's start binary down counter. Now, very interesting thing I am going to teach you. Okay, what I am going to teach you now, using that, you will never have any doubt in this asynchronous counter. This asynchronous counter will become very easy topic for you if you understand this idea that I am going to tell you. Okay, just understand the idea. What we want, just tell me this point. Tell me what we want. We want asynchronous down counter. This is what we want. Okay, asynchronous down counter we want, correct? Down counter, binary down counter we want. Okay, so what we want, so first you understand that this is what we want. So let me assume ABC. Okay, let me assume ABC. What we actually want, we want this binary down counter. We want means we want this type of thing. From 111 we want to go to 110. From there we want to go to 101. There we want to go to 11100. Then we want to go to 011, 010, 001 and 000. And then again where we want to go, again we want to go to 111. Okay, then from here we want to go to 111. Okay, so this is what we want. Now in this, please understand this. Now the question is how to create asynchronous counter. So the idea, everything is in the idea. What is the idea? Can you notice? The idea is this. Can you notice the LSB? Can you notice LSB changing in every cycle? Tell me. Can you notice LSB changing in every cycle? Can you notice LSB changing in every cycle? This LSB changes in every cycle. Can you notice this LSB changes in every cycle? So what this give you? What idea this will give you? LSB changing in every cycle. In every cycle, this LSB changing. So what idea? What the first idea you will get? LSB changing in every cycle. So what is the idea you will get? LSB changing in every cycle. So what idea you will get? That connect LSB directly to clock. Yes or no? Because LSB changing in every cycle. So now you might be thinking, remember, before this idea, some of you might be thinking, sir, why are you connecting clock to LSB? Did you think any one of you thought like this? Please tell me, sir, why are you connecting clock to LSB? Like in the previous examples, we have connected clock to LSB. In these previous examples, you can notice here, we are connecting clock to LSB. So did you think, sir, why are you connecting clock to LSB? Why we are not connecting clock to MSB? So now did you understand why I am connecting clock to LSB? Tell me, did you understand? Because you can notice LSB changing in every cycle. LSB changing in every cycle. Cycle 1, cycle 2, cycle 3. In every cycle LSB changing. So this is the idea, that LSB I will connect to clock. I will directly connect LSB to clock. This is the first idea. What is the second idea? The second idea, what is that? When this second bit is changing, can anyone tell me when this second bit is changing? Anyone want to tell me when this second bit is changing? When the second bit will change? When the second bit will change? The second bit will change when this is going from 0 to 1. When this when this LSB is going from 0 to 1, when this LSB is going from 0 to 1, then this change is happening. Then this change is happening. Yes or no? When this LSB is going from 0 to 1, then this change is happening. This change is happening. You can notice. When this LSB is going from 0 to 1, 0 to 1. When this LSB is going from 0 to 1, change is happening. When this LSB is going from 0 to 1, change is happening. When this LSB is going from 0 to 1, change is happening. Change is happening. When this LSB is going from 0 to 1, change is happening. Okay, at the end, this is 0, 0, 0. At the end, this is 0, 0, 0. So you can notice when the LSB is going from 0 to 1, here also, when the LSB is going from 0 to 1, then this change is happening. Sorry, this change is happening. You can notice this change is happening. So what idea you got? So from this, what idea you got? This is the second idea you got. So first idea was this, the idea. Let's see the first idea. What was the, if you understand the idea, everything will become very easy for you. The idea number 1, LSB changes in every cycle. LSB changes in every cycle. Remember, we are creating binary down counter. Remember what we are creating? We are creating binary down count. This is what we are creating. Okay, we are creating binary down count. So LSB changing in every cycle. So this is the first idea. So what, because of this idea, what you will do? What action you will do? So connect to clock. Directly you connect to clock. You connect it to clock. Okay, next. What is the second idea? The second idea is second bit. I can say second bit. When the second bit is changing, second bit changes when LSB goes from where to where? When LSB goes from 0 to 1. When LSB goes from 0 to 1. When LSB goes from 0 to 1, then the second bit will change. So what should I do? What action should I take? Because of this idea, what action should I take? Because of this idea, what action will I take? When LSB going from 0 to 1. When LSB is going from 0 to 1. So what action I will take? Here it will depend on two things. Please understand, it will depend on two things. It will depend on two things. So here, if you have positive edge triggered flip-flops, tell me, if you have positive edge triggered flip-flops, here, please understand, very simple point. If your flip-flops are positive edge triggered, if flip-flops are positive edge triggered, then what should I connect? If flip-flops are positive edge triggered, then what should I do? What connection I should make? If flip-flops are positive edge triggered, if all the flip-flops are positive edge triggered, if all the flip-flops are positive edge triggered, then you can notice that, then I can directly connect to Q as a clock. Can you, yes or no? So I can directly connect this Q0 to B. Sorry, this Q0 to clock of B. Correct or not? This Q0 to clock of B. Did you understand this point? If your flip-flops are positive edge triggered, then if your flip-flops are positive edge triggered, then for this 0 to 1 transition, it will change because your flip-flop is positive edge triggered. So what it means? It means on this 0 to 1 transition, on this 0, when this LSB is Q0. So when this LSB is going and second bit is B, and second bit is B, this second bit is B. So you tell me, did you understand this? If your flip-flop is positive edge triggered, then what you will do? You will directly connect this Q0 to clock of B. But if your flip-flops are negative edge triggered, if flip-flops are negative edge triggered, then what you will do? Flip-flops are negative edge triggered, means they will trigger when you are going from 1 to 0. So if flip-flops are negative edge triggered, then what I will do? Then I will connect Q0 bar. Very good, Yuvraj. Very good. Yuvraj, very good. So I will connect Q0 bar to clock of B. Did you understand this idea? I am only discussing the idea. Implementation is very easy. Whatever implementation you want, you can create. You can create any implementation if you understand this idea. Just understand this idea. every implementation you can create. Did you understand this point? Please tell me. Please tell me, did you understand this? Anyone has any doubt in this? Let me know. Okay. So remember, so like this. And what about the next? What about the next? So when this MSB will change? Can anyone tell me when this MSB is changing? Can you notice when this MSB is changing? This MSB is changing when this is going from 0 to 1. Can you notice? When this is going from 0 to 1, this MSB is changing. When this is going from 0 to 1, when this is going from 0 to 1, then this MSB is changing. You can notice this MSB is changing. This MSB is changing when for this transition. So because of this transition is happening. So whenever this second bit is going from 0 to 1, you can notice whenever this second bit is going from 0 to 1, you can notice this MSB changing. So this MSB changing when? I can say the third point. What is the third idea? The third bit, when the third bit is changing. So when the third bit is changing, you tell me, when can I say the third bit is changing? That is A. Your third bit, your MSB. Third bit changes when? This third bit is what? This is your A. Okay. So this third bit is changing when? When B is going from 0 to 1, correct? When B is going from 0 to 1, this third bit is changing. When this B is going from 0 to 1, then this third bit is changing. Yes or no? Agree or not? Tell me. Now, tell me if your flip-flops are positive as triggered. If your flip-flops are positive as triggered, remember, please understand this again. This point I am again explaining. The third bit is changing. Third bit should change. This third bit must change when this Q1 is going from 0 to 1. When this Q1 is going from 0 to 1, then this should change. This must change. Okay, now you tell me, if your flip-flops are positive as triggered, then positive as triggered means this is fine. Everything is fine. If you have positive as triggered flip-flop, then what you can do, you can connect this Q1, you can connect directly to clock of A. Okay, and you can notice that similarly, if flip-flops are negative as triggered, then you can connect, in this situation, you can connect this Q1 bar to clock of A. Let me know, did you get it? So these ideas, did you understand? These ideas that we have seen. So very simple. Two situations we got. Remember, we want to create binary down counter. We want to create binary down counter. This is what we want to create. I want to create binary down counter. If I want to create binary down counter. If I have positive as triggered flip-flops, if my flip-flops are positive as triggered, if all my flip-flops are positive as triggered, if all my flip-flops are positive as triggered, what should I do? What should I do? Remember, this is a T flip-flop. So this is a T flip-flop, this is a T flip-flop, this is a T flip-flop, and these are connected to 1. All are connected to 1. All of them are connected to 1. Okay, these are T flip-flop and they will toggle. But the interesting thing is this. You can notice this LSB will toggle in every cycle. This LSB, this is going to toggle in every cycle, and that is fine. In every cycle, this will toggle because T is connected to 1. This T is connected to 1. So this LSB will toggle in every cycle. In every cycle, this is going to toggle. Yes or no? Correct? In every cycle, this will toggle. Now, what is the next? When this should toggle, you just tell me this point. This is your Q0. This is Q1. This is Q2. Tell me when this should toggle. When this should toggle, this should change when this Q0, when this Q0 is going from 0 to 1. When this Q0 is going from 0 to 1. Okay, when this Q0 is going from 0 to 1. So I can directly connect because this Q1 is positive as triggered. This Q1 is positive as triggered. Now, please notice what will happen. Arnab, see what will happen now. See what will happen. This Q1 is positive as triggered. This flip-flop is positive as triggered. Now what will happen? See what will happen. This is positive as triggered. This is positive as triggered. So what will happen? So when the Q0 is going from 0 to 1, it will change. Yes or no? When the Q0 is going from 0 to 1, it will change. Correct or not? When the Q1, when the Q0, because this is positive edge triggered. This is positive edge triggered. What it means? It means when the Q0 is going from 0 to 1, when the Q0 is going from 0 to 1, it will change. And this is what we want. Yes or no? And this is what we want. We want this to change when this Q0 is going from 0 to 1. Let me know. Is this idea clear? Very simple idea. Now, similarly, what we want, now you can notice this is positive edge triggered. This is positive edge triggered. So what I can do, okay, I can directly connect. Now what will happen? What will happen and what we want? Two things you tell me. You tell me two things. What will happen? This is positive edge triggered. This flip-flop is positive edge triggered. So when this Q2, sorry, when this Q1 is going from 0 to 1, when this Q1 is going from 0 to 1, this will toggle. And this is what we want. Yes or no? And this is what we want. So this is the idea. I hope this point is clear. Very simple. Now, similarly, if I have negative edge triggered flip-flop, if my flip-flops are negative edge triggered, if my flip-flops are negative edge triggered flip-flops, if all my flip-flops are negative edge triggered, if my flip-flops are negative edge triggered, then what will happen? If all my flip-flops are negative edge triggered, then what will happen? Remember, this will change. No problem here. So I am connecting all of them to 1. I am connecting all of them to 1. Now you can notice this will change in every cycle. No problem. There is no problem here. There is no problem here. This will change in every cycle. Okay. So it will change in every cycle. I can say this Q0 will change in every cycle. It will change in every cycle. Okay. If I directly connect like this, then there is a problem. Tell me what is the problem? Tell me what is the problem here? If I directly connect like this, what is the problem? What is the problem? Actually what we want and what we are getting. See, this is a negative edge triggered. This flip-flop is negative edge triggered means when this Q0 is going from 1 to 0, it will toggle. This is a negative edge triggered. This is negative edge triggered. What it means? This is negative edge triggered. What it means? It means that when this Q0 is going from 1 to 0, it will toggle. It will toggle. This is what we want or not? This is what we want or not? We don't want this. This is not what we want, Yuvraj. We don't want this. Yes or no? We want when Q0 goes from 0 to 1, then this would change. This is not what we want. Are you getting my point? Please tell me. See, very simple. Please focus. Okay. Please clear your mind. Please clear your mind and focus here. Focus here. This is a negative edge triggered flip-flop. This flip-flop is negative edge triggered. What that means? That means that when this Q0 is going from 1 to 0, this will toggle. But this is not what we want. What we actually want, tell me. We want this. We actually want this. That when Q0 is going from 0 to 1, this should toggle. This is what we actually want. So what should I do? So what should I do? I should make this connection. So I should make this connection. I should make this Q0. I should connect to this Q0 bar. Now everything is fine. Why everything is fine? Tell me. Because now this will toggle when this Q0 bar is going from 1 to 0. Yes or no? Now this will toggle. Now this will toggle because this is negative edge triggered flip-flop. This flip-flop is negative edge triggered flip-flop. So this flip-flop will toggle when this Q0 bar is going from 1 to 0. And that is same as when this Q0 is going from 0 to 1. Both are same. And this is what we want. Arnav, is it clear? See, very carefully, very clear explanation I have given. Now tell me, is it clear? So that is the reason we are connecting this Q0 bar. The same thing we will do here. This is your Q1. This is your Q1 bar. So what I'm going to do? This I will connect to here. Now what will happen? What will happen and what we want? So remember, this is negative edge triggered flip-flop. What it means? It means that when this Q1 bar is going from 1 to 0, it will toggle. When this Q1 bar is going from 1 to 0, it will toggle. And this is what we want, because When this Q1 bar is going from 1 to 0, then this Q1 is going from 0 to 1. Then this Q1 is going from 0 to 1. And this is what we want. So we have seen the implementation of this counter. Understood? Understood or not? Using the idea, everything will become very clear. In the exam, whatever they give you, you can directly do. You can directly do. So what are the binary down counter implementation? Let's see 3-bit binary down counter. What you will do? 3-bit binary down counter. 3-bit binary down counter. 3-bit binary down counter. Okay. So what are the two implementations? If your flip-flops are positive edge triggered, then what to do? And if your flip-flops are negative edge triggered, then what to do? If your flip-flops are positive edge triggered, if your flip-flops are positive edge triggered, what to do? If your flip-flops are negative edge triggered, what to do? So remember, these are T flip-flops. These are your T flip-flops. And remember, this is connected to 1. This is also connected to 1. This is also connected to 1. This is your LSB. This is your LSB. Let's call it Q0. Let's call it Q1. Let's call it Q2. Okay. Now, in this situation, you can notice very simple point. You can notice that I will connect this to clock because it should change in every cycle. This LSB should change in every cycle. So I will connect this to clock because this is positive edge triggered, and you can notice this is positive edge triggered. And what we want that when this Q0 is going from 0 to 1, this Q1 should change, and this will happen. Okay. Similarly, when this Q1 is going from 0 to 1, this Q2 should change, and this will happen. And this will be your final output. This is your binary down counter. Is it clear? This is your MSB. That's it. Correct? This counter will do the binary down counter. Let's do the analysis of this. Let's do the analysis of this binary down counter. So tell me what will happen here. Let's do some analysis of this. So in this binary down counter, initial state is 1. Let's assume initial state is 111. Let's assume initial state is 111. Let me assume initial state is 111 or maybe 000, whatever. So let me assume the initial state is 000. Then tell me what will be the next state. Actually, what should be the next state? You can make the transition diagram. Using the transition diagram also you can understand if you want. Okay, for the last time I will create this transition diagram. After this we will not see this transition diagram again, but please understand this example. Okay, this is your binary down counter implementation. Now let's see what will happen in this binary down counter. So let me give you a clock pulse. Let me give you the clock pulse. Okay, this is the clock pulse. So tell me what will be the output for Q0, for LSB, for Q0, what will be the output? Tell me for Q0, what will be the output? For Q1, what will be the output? And for Q2, what will be the output waveform? Tell me. If there is no propagation delay, assume no propagation delay. Assume no propagation delay. Assume there is no propagation delay, then what will be the output? Tell me, quickly tell me. This Q0 will toggle because your flip-flops are positive edge triggered. Your flip-flops are positive edge triggered. Initially, let me assume this is 0. Initially, let me assume this is also 0. Let me assume this is also 0. This is also 0. This is also 0. So initially, I am assuming these are 0, 0, 0. Now you can notice with every clock cycle, this will change. With every clock cycle, this will change. Correct? With every clock cycle, this will change. Yes or no? It will change with every clock cycle. It will change with every clock cycle. Okay. Now, after this, what? Now you can notice this Q1. When the Q1 will change, tell me. When the Q1 will change, when the Q0 is going from 0 to 1, because these are positive edge triggered. Because these are positive edge triggered. All of them are positive edge triggered flip-flops. These flip-flops are positive edge triggered flip-flops. All these flip-flops, these are positive edge triggered flip-flops. Okay, so you can notice when the Q0 will go from 0 to 1, then this will change. Now what will be the output? So in this situation, this will change when it is going from 0 to 1. When it is going from 0 to 1, it will change. When it is going from 0 to 1, it will change. Why it is changing? Because we are fixing t equal to 1. Yes or no? Why it is changing? Why? What is the reason it is changing? Because we are fixing t equal to 1. This t equal to 1 is fixed. So with every rising edge, this will toggle. With every rising edge, this will toggle. With every rising edge, this will toggle. Okay. So now you can notice this will happen. Now with every rising edge, this Q2 will also toggle. This Q2 will toggle with every rising edge of Q1. With every rising edge of Q1. Okay. So finally, what output you got? What is the output that you got? So I can say this is what you are getting from 0, 0, 0. Where are we going? From 0, 0, 0. Where are we going? We are going to 1, 1, 1. Okay. So from 0, 0, 0, from this state, we are going to 1, 1, 1. Where are we going next? Remember, this is MSB. Remember, this is MSB. This is your MSB. Okay. So the next state is your 1, 1, 0. The next state is 1, 1, 0. What is the next state? What is the next state? That is your 1, 0, 1. That is your 1, 0, 1. What is the next state? After 1, 0, 1, the next state is 1, 0, 0. The next state is 1, 0, 0. After the next state, what is the next state? That is 0, 1, 1. The next state is 0, 1, 1. And everything will go like this. Okay. And so on. And so on. And so on. And then finally, I can say that from 0, 0, 1 to this. This will happen. Did you get? This is your binary down counter. This is your timing diagram. And this is how you can do. Okay. Very simple. Now, one more very interesting thing. If there is propagation delay, because in the real life, there will be propagation delay. Yes or no? If propagation delay, if there is a propagation delay of flip-flop, if a flip-flop propagation delay is non-zero, if flip-flop propagation delay is not zero, then what will happen? Then what will happen? Let's see. In this situation, what will happen if the propagation delay is not zero? So in this situation, you can notice this Q0 initially, let's assume this is zero. Initially, let me assume initially this is zero. Initially, this is zero. Initially, this is zero. Initially, I am assuming they are 0, 0, 0. Now, at this time, this should change, but it will change after some time. 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 Okay. Now you tell me. So what propagation delay is here? Tell me. Can anyone tell me what is the propagation delay that we have here? Which propagation delay we have here? This delay. This propagation delay. What is that? This is equal to T. Is equal to T. Let's assume the propagation delay of every flip-flop is T, which is non-zero. Then tell me. Then this propagation delay is T. Yes or no? This propagation delay is T. I can say this propagation delay is T. Okay, this propagation delay is also T. Now let's make the waveform for Q1. What Q1 will do? Q1 will change on these edges. On these edges, Q1 will change, correct? On these edges, but actually it will also take some time. It will also take some time. It will also take some time. Okay, it will change, but after some delay, after some propagation delay. So it should actually change here, but after some propagation delay, it will change. After some propagation delay, it will change. Now you tell me one more thing. Okay, now you tell me what will happen. Okay, now in this situation, tell me what is this propagation delay from the clock point of view. From the clock point of view, from the clock, how much far you are? From the clock, how much far you are? From the clock, that is propagation delay. You can notice this propagation delay from the clock with respect to clock, with respect to clock, with respect to clock, that is 2T. That propagation delay is 2T. Yes or no? This propagation delay, if you notice, this propagation delay is 2T. This is your propagation delay 2T from clock point of view. So this propagation delay is increasing. Agree or not? This propagation delay, this is increasing. This is increasing. Now what will happen with Q2? What will happen with Q2? In Q2 will also change, but Q2 will also change after some time. After some time, after some time, after some delay, it will change. So again, the same thing. Again, the same thing. Tell me what is this propagation delay from the clock point of view? From the clock point of view, what is this propagation delay? This propagation delay. What is this propagation delay from clock point of view? That is 3T. Now That is 3t, right? Why 4t? From only 3t. Look at this, only 3t. Here t, then another t, then another t, t, another t, another t. This is t, this is another t, another t. So there is 3t. Yes or no? Is it clear? See, this is t, this is double t, this is triple t. Is it clear? So here you have t, here you have double t, and here you have triple t. So that the propagation delay is increasing. So that's it. This propagation delay is increasing. Now, one more very interesting thing. One more very interesting thing. So if you have n, and let's assume you have n devices. Let me assume you have. So now this is a node that you want to study. This is a node. Let's focus. If you have n devices, n bit ripple counter, then what will happen? If you have n bit ripple counter, what will happen? What will be the propagation delay? Like the final propagation delay, what will be that? If you have n bit ripple counter, this is your clock, this is your clock. Let's assume your clock is like this. So let's assume your clock is like this. Your clock is like this. Let's assume this is your clock, and so on. So what will be the, I can say, MSB propagation delay? For MSB, what will be the propagation delay? For MSB, what will be the propagation delay? That will be NT, that will be NTP, then that will be NTPD. Yes or no? It will be NTPD. What is TPD? This is your one flip-flop propagation delay. Correct? This is your one flip-flop propagation delay. Now, can you notice one more thing? Just tell me this point. Just tell me this point. If you have, can you notice this is closing to the next positive edge? Can you notice this is closing? If you have n, if you have n, if you have n, if you have qn, if you go like this, if you have qn, if you have qn, let's assume very big number. This qn is large. Let's assume. Then what will happen? This propagation delay will almost cross this boundary. This next clock is, yes or no? This will be the propagation delay. This will become the propagation delay. Yes or no? Because the propagation delay is increasing. It is continuously increasing. If you have n ripple counter, sorry, if you have n flip-flop in the ripple counter, in the asynchronous counter, if you have n flip-flop, then this propagation delay will keep increasing. If this n is increasing, this final propagation delay, this will keep increasing, and there will be a problem. What is the problem? If it will cross this, if it will cross this boundary, then uncertain behaviors will start happening. Yes or no? If it will cross this boundary, if we cross this boundary, means basically, if we don't settle within this boundary, see, here you are settling within this boundary. Within this boundary, you are settling. Yes or no? Before this boundary, this is the boundary. Let's call it boundary. This is your next boundary, I can say. This is your next clock edge. So before that, we are settling. Yes or no? There is propagation delay, but we are settling. But you can notice, if you increase the number of flip-flop in the ripple counter, then this settlement will not happen. Yes or no? If you increase after a limit, if you increase, then this settlement will not happen. The next clock edge will come and you are not settled. The next clock edge will come, but you are not settled. It's like your next midterm, your next weekly quiz will come, but you have not covered the pending chapters. You are not settled. Then uncertain behaviors will start happening because you are not ready. Next clock edge will come, but your system, your circuit, this is your circuit. Your circuit is not settled. Okay, tell me, is this clear? So this is the idea. So what should happen? So tell me, for proper functioning, what should happen? What the maximum in the ripple counter? Now you tell me, in the ripple counter, what is the maximum number of flip-flops you can have? So tell me, what is the maximum number of flip-flops we can have? This is my question. What is the maximum number of flip-flops we can have? We can have in ripple counter. We can have in a ripple counter. We can have in a ripple counter. Ripple counter means asynchronous counter. So maximum how many flip-flops we can have? Tell me. That will be, I can say this definitely must be less than equal to your clock period, your time period of clock. Yes or no? This should happen. This should happen. So maximum, this is the relation. This should happen. For a proper functioning, this relation, this should happen. In any ripple counter, this should happen. In any ripple counter, remember, in any ripple counter means this your asynchronous counter. In any ripple counter on n flip-flops, if there are n flip-flops, then what should happen? For proper functioning, what should happen? Tell me. For proper functioning, what should happen? This should happen that this n into TPD, this must be less than equal to your clock period time. In the terms of frequency, what I will write? In terms of frequency, what should happen? If I want to find the frequency, then this will change because you will divide by 1. So this period time must be greater than this. So frequency must be less than this. What I can say? I can say frequency should be, so the frequency of clock, what that should happen? That should be less than equal to 1 by NTPD. Yes or no? 1 by NTPD. Is this clear? Let me know. Many questions are there in the GATE exam on this point. Did you understand this point? What is happening? Because of propagation delay, it is increasing. The propagation delay is continuously increasing. Can you notice? Like you have here, like in this, you have three flip-flop. There are 3 flip-flop, and you can notice here you have T, here you have 2T, here you have 3T. So the propagation delay is continuously increasing. If this n is large, then what will happen? If this n is large, then it will cross the boundary. It will cross the next clock edge, and there is a problem, and that is the problem. So finally, this is the point we can say. Okay, very good. So if you understood, very good. And one more thing, what are the transient states? Let's also focus on the transient states. So tell me, what are the transient states? Because of this, how many transient states you are getting? So let's see. If propagation delay is there, if a propagation delay is non-zero, then there will be transient states from 0, 0, 0. Actually, where you should go? Tell me. From 0, 0, 0, where you should go? You should go to 1, 1, 1. But actually, what will happen? First, this will change, right? So you will go to 0, 0, 1. First, this will change. Then the next bit will change. Then the next bit will change. And finally, the next bit will change. And you can notice this in this timing diagram. In this timing diagram also you can see, is it happening? In this timing diagram, before going to 1, 1, 1, before going to this 1, 1, 1, what is happening? Before going to this 1, 1, 1, see this. See this. For a moment, this is 0, this is 1, this is 1. And before that, what is there? Before that, this is 0, this is 0, this is 0, this is 0, and this is 1. This is 0, this is 0, this is 1. So you can notice 2 transient states we got. Yes or no? You can check in the transition diagram. In the transition diagram, you can see that we got these transient states. 2 transient states we got. Where should I go next? What should be my next state? What should be my next state? That should be 1, 1, 0. Will there be any transient state? Will we have any transient state? No. Okay, can you verify from the timing diagram? Can you verify from the timing diagram? Do we have any transient state? There is no transient state. From 111, we are directly going to 110. Very good. What should be the next state? What must be the next state? The next state must be 101. How many transient states will be there? Number of transient states. So first LSB will change. First LSB will change. First LSB will change. Then this second bit will change. So yes or no, this 111, this will be the transient state. And you can verify from the transition diagram. Verify from the transition diagram. Tell me, verification from the transition diagram. Is there any verification? This is your 101, but this is the verification. Look here. 111. Transient state we got or not? Tell me. Yes, we got this transient state 111. Okay. Similarly, after this 111, where you should go? Where you should go? You should go to 100. Will there be any transient state? Will there be any transient state? No. Only one bit is changing. Only one bit is changing. So no transient state. Can you verify from the transition diagram? From the transition diagram, can you verify? Yes, you can verify. There is no transient state from 101 to 100. There is no transient state. Where should I go? From this. From this, where should I go? I should go to 011. Maximum number of transient states will come now. Yes or no? I should go to this. Maximum number of transit states will come now, because first this will change. First this LSB will change. Then this, then it will become 111, and then it will become 10011. So two transit states are coming. Again, two transit states. How many transit states from 011 to 010? How many transit states between this? For this transition, how many transit states? There is no transit state. 0. For this transition, how many transit states? How many transit states for this transition? For this transition, how many transit states? 1. There will be one transit state. First LSB will change. First LSB will change. Then the second bit will change. Okay, very good. And finally, finally this will happen. No transit state. Is this chapter very easy for you now? Tell me. Is this chapter like finding transit state? What are transit state? What is ripple counter? How to create ripple counter? Okay. If you have positive edge triggered flip flop, then how to create ripple counter? If you have negative edge triggered, then how to create ripple counter? Kushal is saying too logical. Normally, people don't study this digital logic in this logical manner. Kushal, this happens. Have you seen, like, I invite you to watch lectures on internet. Okay, you watch some lectures on internet. People don't study this digital logic in a logical manner. The name is digital logic, but people don't study this digital logic in a logical manner. Okay, so normally what students do, what many students do, they have a circuit and they will take some examples. They will take some examples and they will understand the circuit, what the circuit is doing, and that's it. This is enough. But if you understand this concept, all the concept, every concept, if you understand in a logical manner, logically, if you think, then these concepts will become very easy for you. Okay, these are extremely easy concepts. Let me tell you, extremely easy concepts. And you will find interest in this subject. Like sequential circuit, let me tell you, this sequential circuit is the, for the majority of the GATE aspirants, this sequential circuit is very complicated topic. Many GATE aspirants you will find who will say, I don't understand sequential circuit. I cannot solve the questions of sequential circuit. But this sequential circuit is extremely easy topic, extremely. Okay, this once you understand it. So once you understand this in a logical manner, it will become very easy for you. So far, did you understand everything? Please tell me. So we have seen everything. We have seen all the things we have seen. Okay, so let's just recap. Now, whatever we have seen, that is the recap. This is your 3-bit down counter. Is this correct? Look at this and tell me, is this correct? Look at this and tell me, is this correct? Is this correct? Look at this and tell me. What you want in a 3-bit down counter? Tell me what you want in a 3-bit down counter. You have 3-bit down counter. So this is your Q2, this is your Q1, this is your Q0. In this, what you want? You want this to change every cycle. This should change in every cycle. This is what you want, yes or no? This should change in every cycle. This is what you want. This is what you desire, yes or no? Correct? This should change in every cycle. Okay, next. When this should change, tell me. This is your down counter I am taking. I am talking about down counter. Remember, I am talking about down counter. We are talking about down counter. Down binary down counter. Okay, so what should happen? Like from 111, you should go to 110, then you should go to 101, then you should go to 100, then you should go to 011. So you can notice that when this Q0 is going from 0 to 1, when this Q0 is going from 0 to 1, then this transition should happen. Then this transition should happen. This changes should happen. This changes should happen. So you can notice this Q1 should change when this Q0 is going from 0 to 1. Is it happening in this diagram? Remember, your circuit is positive edge triggered. Your flip-flops are positive edge triggered flip-flops. All the flip-flops are positive edge triggered flip-flop. This flip-flop is positive edge triggered flip-flop. So you can notice that when this Q0 is going from 0 to 1, because this flip-flop, this second flip-flop is positive edge triggered flip-flop. Okay, this is your Q2. Sorry, this is your Q1. This is your Q0. This is your Q2. So this all the flip-flop are positive edge triggered flip-flop. So when this Q0 is going from 0 to 1, this will toggle because we are connecting 1. Remember, everything is connected to 1. All the T inputs are connected to 1. All of them are connected to 1. Okay, so this is what we want, yes or no? When the Q0 is going from 0 to 1, we want this Q1 to change. We want this Q1 to change. This is what we want. So that is the reason we are doing this. And when should Q2 change? When should Q2 change? Q2 should change when Q1 is going from 0 to 1. See, Q2 should change when Q1 is going from 0 to 1. When this Q1 is going from 0 to 1, Q2 should change. Okay, so I can say that this Q2 should change when this Q1 is going from 0 to 1, from 0 to 1. And you can notice all the flip-flops are positive edge triggered flip-flops. So this will happen. So this is your binary down counter, yes or no? Very simple. Okay, so this will happen. This will change in every clock. So the first flip-flop will change. The first flip-flop is what? Tell me. The first flip-flop is your LSB. So the LSB will change on every positive edge of the clock. Why positive edge of the clock? Because these are positive edge triggered flip-flop. All these flip-flop are positive edge triggered flip-flop. The second flip-flop will change on the positive edge of Q0, and the third flip-flop will change on the positive edge of Q1. Very simple, this topic. Okay, now you can notice these waveform. So these waveform you can see, and the propagation delay is increasing. Waveform we have already seen. So you can read these, correct? These slides you can read. All these slides you can read. So you can notice the propagation delay is increasing. If you notice, see here the propagation delay is T, correct? Can I say here the propagation delay is T? There is some propagation delay that is T. Okay, some propagation delay that is T. Now the propagation delay has become what? That has become double T. Can you notice the propagation delay has become double T? Now the propagation delay has become triple T. Triple T. Okay, now the propagation delay has triple T. So can you notice propagation delay gets longer? See this. Very nice slides these are. These are very nice slides, yes or no? Okay, so these slides are taken from a university. There is a IOWA university. From this university, I have taken all these slides. Okay, so credit goes to them. All these slides are from this university, Professor Alex. Professor Alex. Okay, so these slides are taken from this university. And these are excellent slides. So I want to give this thank you to Professor Alex. Actually, what happened, let me tell you. So Professor Alex, they removed these slides. So in 2018, I used to study from these slides. In 2018, 2019, I used to study from these slides. The digital logic I have studied from these slides. Okay, so when I was in ISC at that time. Oh, after that, what happened? So these slides were removed by Professor Alex, and I sent a mail. I requested them. So like a few months back, I requested them to please re-upload the slides. So they had already removed it from their website. All the slides were removed. So I sent a mail. I requested that please kindly upload the slides because the slides are extremely nice. Okay, so and then they again re-uploaded. So anyway, so let's see. So let me keep it here. Okay. So slides. Okay, let's see the next. So hopefully all these things are clear, right? Okay, so now actually we should finish this topic. Should we take a break or let me finish this topic? Should we finish or should we take a break? Let's take small break, 5-minute break we can take, and then we can finish it because it will take I think 1 more hour because there are many questions. Let me tell you, on this asynchronous counter in the GATE exam there are many questions, a lot of questions. Okay, some of those GATE questions we will solve in this today we will solve, and some questions I will give you as homework and you can solve them. So there are many questions on this asynchronous counter. Let's take a small break, only 5-minute break we will take, and then we will I will recreate a new session. Okay, so basically in the next session what we will study in the next session, we will study binary up counter. So this up counter we will create. Okay, first we will, so next session, in the next session what we are going to study in the next lecture. So I will create a next new lecture. I will create in the next lecture. We will create, first we will create binary up ripple counter. This binary up ripple counter we will create. Okay, after this we will study. Okay, so with this we will study. Then after that we will study cascading of counter. This concept we will study. How can we cascade ripple counters? Cascading ripple counters. So if you have some ripple counters, multiple ripple counters, if you have multiple ripple counters, how can you connect them together? Okay, so this concept we will study. We will study very interesting point. Can you notice in the binary counter what is the sequence? In the binary counter, what is the sequence? This is the sequence, like 0 to binary up counter. This is the sequence, right? 0 to, for example, 15 and then to 0. This sequence we are studying right now. Yes or no? Agree or not? This sequence we are learning right now. Right now we are learning this sequence. But now you might be thinking, sir, how can I count? Like if I only want to count from 0 to 9 or from 0 to 6 or from 0 to 5 or from 0 to 12, then what to do? Means counting from 0 to m only. Means how to create this type of situation, like 0 to 2 and then maybe 0 to 6 only, 0 to 6 and then back. How to create this type of counters? Okay, now what is the next question you might be thinking? Tell me, what is the next question you might be thinking? You might be thinking, sir, how to create from anywhere to anywhere? Like if I want to go from 3 to 6, if I want to go from 3 to 7 and then I want to come back, then how to do that? Okay, how to do that? Yes, preset and clear concept will come. So these concepts we will study after the break, and then we will solve the some GATE questions. Some GATE questions we will solve. After that, we will solve 4 or 5 GATE exam questions we will solve on the ripple counters. Okay, so these topics we need to study. Means counting from 0 to any number m, and counting from anywhere to anywhere. Counting from anywhere to anywhere. These things we will study, and then we will solve some GATE exam questions. Okay, this we will study in the next lecture. I will create the next session in 10 minutes. So you take a 10 minutes break. So we will reach, or maybe you can take a dinner break. Okay, take a dinner break. We will start at 9. Okay, 9, 10, 40 minutes break. Is this clear? So dinner break you can take. 40 minutes break. We will start at 9, 10. Okay. If anyone has any doubt in this lecture, then you can ask at the end of the next session. Okay, but I hope you understood whatever we have seen. I hope you understood, because all these concepts, all the transient state and all these things we have already seen in the previous lectures. Okay, so after 40 minutes, after the dinner break, we will start again. Okay, thank you.